Good morning, Mr. President, Mr. Chancellor, and colleagues. I'm giving a brief introduction to what is happening today in nanoscience and technology. For those who have not worked in it, I'll take the first few minutes to introduce this topic in a very simple way. Nanoworld is not new. Many years ago, many centuries ago, the Lycurgus cup was made where the cup changes the color when it is held up to light. The cup is opaque green. When the light is shone through it, it turns to a glowing translucent red cup when the light goes through it. And this is due to very small particles of colloidal gold inside the glass. This is a cup you can even now see in the British Museum in London. It is really an example of nanoscience practiced long ago. Oh boy. Well, in the Roman period, colloidal metals were used to dye fabrics, color glass, to treat diseases, but they did not know that they were dealing with nanoparticles of metals. They are doing this operation without knowing exactly either the size of the particles or the various aspects of these wonderful particles which gave these colors and so on. Purple occacius, very well known, the Maya blue, many of them had nanoparticles in them. So this is historical aspect of, oh boy. Oops. The famous story of Damascus sword came out a few years ago. The Damascus sword were first made in the 8th century. They were very famous for their strength and sharpness. Peter Pofler in Germany did a microscopic analysis of it recently and found that actually the reason Damascus swords were as strong and as powerful was because they were made of a steel called a wood steel. Wood steel was made in India in 300 BC. And without knowing, the Indians were making the steel in such a way that nanotubes, carbon nanotubes, were getting incorporated in the steel. In fact, this is a very nice microscopic work done by Pofler in Germany quite recently. So these are all old examples of nanoscience in operation, without knowing that they were dealing with nano. The first scientific experiment on nanomaterials was done by the greatest scientist of all time, Michael Faraday. In 1857, he made metal particles, nanoparticles, and you can see in those bottles, these are the samples made by Faraday, even now preserved in London. And these are gold particles. He made platinum particles. And he did not again know the dimensions of these particles. He said, he called them divided metals. And divided metals, he said, are different from metals, and that's where it stood at that time. Nanoworld, of course, you know, we are dealing with a nanometer, 10 to the power of minus 9 meter, or 10 angstroms, very, very tiny. And of course, the area is supposed to have got big boost because of Feynman's famous lecture in 1959, where he talked about there is plenty of room at the bottom. Today, unfortunately, nanoscience is no longer as simple as it was, say, 10 years ago. It has become very competitive, very popular, very sophisticated, and it also has several highly important accomplishments I'll talk about. Again, to remind you, in nature, there are examples of nanomaterials like magnetotactic bacteria with beautiful, nice particles, nanoparticles of magnetite, Fe3O4, in the bacteria. And this is the famous example from Hewlett-Packard when they made this wonderful quantum dot, this is the scanning tunneling microscopic image of a quantum dot found by assembling a few atoms of germanium, the germanium pyramid. This became a very impressive thing. In fact, for those who may not know, Bill Clinton, when he was president, this picture and the next picture I'm going to show were shown to him, and he got so impressed, he gave a nanoscience, a big boost to the United States at that time. This picture, therefore, has historical, sort of historical meaning. This is the more interesting picture of IBM at the same time, which Bill Clinton saw when he saw these 48 atoms forming a coral, and people had arranged this beautifully in the laboratory. And they said, my God, how can atoms be arranged so nicely? This is nanoscience, you see. And this is the early history, not very early, in the last 10, 15 years, this is the history of nanoscience. Let me tell you what nanomaterials are. We have zero-dimensional nanomaterials, what we call quantum dots or small particles, which are nano in all the three directions, the X, Y, and Z directions. We have got one-dimensional nanomaterials, the nanowires, nanotubes. They are nano dimensions. They are nano in dimensions in two directions. And then you can have films, nano sheets, which are only nano in one dimension. So all these materials are very, very important. I just am showing you every kind of thing you can think of. In one frame, I'm showing you the nanocrystals, all kinds of metals have been made, oxides, nitrides, sulfides, nanowires of all kinds of materials, metals, oxides, sulfides have been made, nitrides, and so on. Nanotubes were first made out of carbon. Of course, since then, a number of inorganic nanotubes have been made, an area where I myself have contributed quite a bit. And then, of course, we have nanofilms, two-dimensional films. A number of types of films have been made. The most important one, of course, is the last one, graphene, which has really become a very big flavor of the day today. Well, let me remind you, Fullerenes were discovered in 1985 in the laboratory, actually made in the laboratory in 1990 in Germany. Because my friend Harry Kroto and Smalley in Texas got a Nobel Prize for this. You see, the Fullerene dimensions are just about 0.7 nanometer. The C60 has a diameter of about 0.7 nanometer. So we're dealing with a molecule which is already a bit of a nano. It is sort of a nano molecule. So I'm trying to remind you of that old. And then you see nanoparticles of various shapes and sizes have been made. You can make hexagonal particles, spherical particles, rectangular particles, triangular particles. We have now technologies or methods of making all kinds of particles of all kinds of shapes and dimensions in the nano regime. Now, one of the main things to remember is properties depend on size. Of course, when people like me are large objects, usually properties do not change much with size. However, there is a regime when properties can vary linearly with size in a particular small dimension. In the nano dimension, however, particles change with size in a very peculiar way because we get quantum effects. These quantum effects are so prominent that nanoworld is dominated by these quantum effects. For example, this is a well-known example. Everyone shows this frame to talk about size as an important parameter in nanoscience. Here I'm showing cadmium selenide nanoparticles. It's the same material of different particle sizes. Look at different colors it gives when it is excited by some ultraviolet light or visible light. For example, the green colored cadmium selenide, that green light comes when the size of the nanoparticle is 3.5 nanometers. The red color comes when the size of this cadmium selenide nanoparticle is just 5 nanometers. Very small change, 3 to 5 nanometer change gives you green or red. In fact, you can mix these colors, you can produce white light out of cadmium selenide nanoparticles. Well, let me tell you in words, I've limited the number of frames because the time I have. You see, let us take gold. If you have a block of gold or gold in my ring, it has the same properties. However, if you make a small particle of gold, say 1 nanometer or 2 nanometer particle of gold, it is no longer the same. It becomes very reactive. It is no longer metallic. Gold ceases to be metallic when it has about 200 atoms or something like that, around 1.5 to 2 nanometers and below. And this is one experiment done many years ago in Israel and also in my laboratory. In mercury, for example, this is actually some sort of spectroscopy, photoemission spectroscopy. What it is doing is taking different number of atoms of mercury and see there is a gap between two states, electron states here. See, that gap is very large when you have 3 atoms, n equal to 3. The gap is smaller when n equal to 8. That means mercury is not metallic. When n equal to 30, still there is a gap between those two features you can see in the spectrum. N equal to 100, still there is a gap. It is only about 250 around that atom, mercury becomes metallic. In other words, any mercury cluster which has less than 300 atoms or 250 atoms is non-metallic. The non-metallic properties of normal metals is very important in surface science. In many areas, people do study properties of such small particles of metals. One of the major discoveries from my laboratory in the last 3-4 years, I want to mention it, I'm not going to share frame, is doesn't matter what inorganic material you have, zinc oxide, aluminum oxide, magnesium oxide, any material which does not have any magnetic ion, but still it will show ferromagnetism in the nano regime. In other words, small particles of zinc oxide, aluminum oxide, magnesium oxide also ferromagnetic hysteresis. And this is a very interesting property of surface ferromagnetism that has come in the last 2-3 years in small particles. We still do not know. Here is a very interesting thing. We do not know why. Exactly why do we get magnetism without having magnetic ions in small particles? We do not know that. Exactly. Well, I'm not going to give an exercise just to show. Today we can use whatever chemistry. I'm just showing one example of cadmium sulfide. You can use some chemistry. And what is interesting, you see that cadmium sulfide nanoparticles, you can disperse them in any organic liquid, and you can see the solutions of these of these nanoparticles of cadmium sulfide in an organic liquid. What we normally do is, what is one normally does is, once it is made, you do an electron microscopy. You can see on the bottom right-hand side, one particle of cadmium sulfide is shown where you see the lattice planes, and so it is a single crystal. Each particle is a single crystal. You can study all the particles. You can then study structure. And one of the nice things about nanoscience is when the particle size is small, you get metastable structures quite often. You don't get the more thermodynamically most stable structure. And a lot of studies have been made in this direction. And here is a very simple experiment. For example, if you take two liquids, like an oil and water, say benzene and water, don't mix, but at the interface, you see, between the organic liquid and water, you can make very thin layers, which are two-dimensional sheets of nanomaterial. For example, you see, I show nanocrystalline films of gold. The particle size can vary based on concentration, temperature, a number of things, and you can make beautiful nanoparticles, nanocrystalline films at the interface. The interface being so thin, you always get a nanofilm. In fact, this technology has been used recently to make beautiful single crystalline films at the interface. In fact, I show this, don't worry about all the things in this picture, it is very busy. On the bottom left-hand side, you can see one picture of a sulfide with lines in it. That entire film across the interface is a single crystal. And you can see the black spots in the diffraction pattern. And it's very difficult to make such films by ordinary physical methods. You do in physics, you do evaporation, you conserve all kinds of technology. You will not be able to make it. Here is a beautiful nanofilm, which is single crystalline at the interface. So a lot of this kind of work has been done in the last few years. It's very interesting. And I'll now leave these nanoparticles and nanofilms of this kind and would mention to you about carbon nanotubes. For those who may be interested, carbon nanotubes were made long, long ago in Russia, but nobody noticed it for some reason. And it was made again in 1976 by my friend Endo in Japan. Again, nobody noticed it. But it got noticed only in 1991 when my other friend Ijima in Japan did this beautiful electron microscopy of it. In fact, everyone credits Ijima as having discovered carbon nanotube. It's not correct, actually. Endo and others had done it, but it is Ijima who characterized the nanotube properly in electron microscopy and so on. And these carbon nanotubes were made by arc evaporation of graphite electrodes. And what I show on top are multi-walled nanotubes. The one in the bottom you see are bundles of single-walled nanotubes. Single-walled nanotubes are very fine capillaries of 1 to 2 nanometers in diameter generally, or 1 to 5 nanometers, with no graphitic layers on them, and you can make them all in the laboratory. And here is something where you have millions of nanotubes aligned in a particular way. In the bottom left, you see they're aligned perpendicular to the screen, And so you have millions of nanotubes, exactly the kind of nanotube agglomerate that you need for using them in field emission and many such applications. Well, here I want to leave carbon. You see, many of us think carbon nanotubes, Fullerene, they all have to have carbon. But many years ago in Israel, in Weizmann Institute, my friend Tene showed that Fullerenes, even though they were first made of carbon, can be made of inorganic layered materials, which are also just like graphite. See, Fullerene is derived from graphite by arc evaporation of graphite. Why not make a similar layered materials in inorganic? So molybdenum sulfide, boron nitride, they all have structures similar to graphite. So inorganic Fullerenes were made, and this is an example of one of the pieces of work Tene and I did some time ago, where you can see the beautiful circular, the layered structures of inorganic Fullerene made in the laboratory. Then, of course, nanotubes. Nanotubes are no longer made of carbon, but you can make all kinds of inorganic nanotubes. In fact, recently I have a perspective, not very recent, about 3 years ago, a perspective in advanced materials, and we have a whole family of inorganic nanotubes with very, very interesting properties. I do not have time to go through the properties today in detail. We can also make a whole bunch of nanowires, oxide nanowires, nitride nanowires. You see, each nanowire, the one in the bottom you see in the electron microscope picture, each nanowire is a highly single crystalline material. You can see the lattice planes, and you can make wonderful nanowires today by various techniques. Okay, I have covered what has happened in 15 years in 10 minutes, but I want to come to today, what has happened in the last 6 years. For those, I'm so glad that Dr. Phillips, Bill Phillips did mention high temperature superconductivity. I am one of those practitioners at that time in the 1980s, late 80s. It was the biggest sensation that physical sciences saw at that time. I think there were something like about 100,000 printed pages of journal space that took at that time. Well, almost as much of a sensation has been caused by graphene today. Graphene is a single sheet of carbon atoms, all 6-membered rings, two-dimensional. It's a really 2D system. And see, we call this 2D, this sheet on top, as the mother of all graphitic forms, because if you have this sheet, you can stack it on graphite, you can roll it and make a nanotube, you can even make a buckyball out of it. So this is the most, elementary form of carbon you can ever have, which is a single sheet of carbon. People have tried to make it for years. For those who may not know history of this thing, even 50 years ago there were attempts to make single sheet of this. The sheet is only 3 angstrom, 3.4 angstrom, very, very thin. How do you make it? But they were not succeeding in making it until, of course, recently, about 5, 6, 7 years ago, these two, the Russian friends in Manchester did this. See, in graphene you have a single layer, you can put 2, you can call it a bilayer, you can have a few layer graphene. Well, less than 10, if you have more than 10, it's more like graphite. So you can have all these graphenes. So what they did was, you take a sheet of, a single crystal of graphite, take a scotch tape, peel off the top layer. Of course, someone like me with we put a lot of pressure on the graphite, you get many layers off. We delicately touch it to get one layer sticking to the scotch tape. And you study that single layer, and you measure the height of that. It may have 2 layers, a single layer, and you can do the microscopy of various kinds on that. Well, graphene, by chemistry, a lot of methods have been there in the last few years. We've given some references, don't worry about it. In the last 2-3 years, there are many methods for making single layer or double layer, 2-layer graphene. And we can also make ribbons. You know, graphene is a sheet. Suppose you want to have a ribbon, a small ribbon, a rectangular ribbon. You can't take graphene and cut it with scissors. You have to find a way of making it. One of the ways we have made, which is very clean graphene ribbons without any surface contamination. Because most people use oxidation of nanotubes using permanganate, acid, and so on. But that is not very good because it gives a lot of oxygens at the edges, and we don't want that. I hope you know that when you have a sheet of carbon, there are edges. Edges have many properties. And you have ribbons, there will be more edges for the same mass than even sheets. So ribbons have very interesting magnetic properties. Our method of making ribbons involves laser irradiation of a nanotube, unzip the nanotube. I hope you can see that in the picture in the bottom of this frame. Well, many interesting properties have come, and for those, again, since I'm getting old, I remember this, my very good friend Millie Dresselhaus, a number of people like that, 50 years ago used to worry about properties of graphene. Nobody looked at it because there was no experimental measurement. Now I can tell you, whatever graphene you make is magnetic. It is ferromagnetic. And well, don't worry about the details of, it is actually like a frustrated system. It's a ferromagnetic interaction superimposed on a background of antiferromagnetism. It is like in a frustrated system. There are many such systems in solid-state physics and chemistry. And I show the typical hysteresis loops. Not very large magnetization, but still you get this wonderful ferromagnetism in these materials. This is a paper I had in PNAS sometime about 3 years ago, which I think is very interesting. You take graphene, small amount of graphene, put it in a polymer, make a composite, mix with that a very small amount of one-dimensional nanotubes or zero-dimensional nanodiamonds. So in other words, you would have put in a two-dimensional graphene along with a one-dimensional or a zero-dimensional nanocarbon. When you do that, you get enormous synergy in mechanical properties of composites. We tried to show that a few years ago. And this is another very interesting use of graphene. Well, you can dope graphene. I will not talk too much about it. You can dope it with boron. You can dope it with nitrogen. You can make it P-type or N-type graphene. And it has wonderful field emission properties. It has very low turn-on field emission. I hope people will use it because it is easier to make graphene than carbon nanotubes, which are being used. And I think this is something of the future. I hope in the near future there will be some applications in this area. And we have made very, very nice infrared detectors using graphene oxide. As you know, graphene has no gap, the gapless material. So introduce a small gap using the so-called reduced graphene oxide. It's a small gap. And it is just about corresponds to the energy of infrared radiation. It is a very good IR detector. In the bottom left-hand side, you will see by using a hand, you put a hand in front of a detector, you get the signal. In fact, you need not have fever, otherwise you can have even bigger signal. With ordinary hand, you can get wonderful infrared detection with these kinds of reduced graphene oxide detectors. Well, most of these contaminated graphenes, or slightly oxidized graphene, give blue light, and this blue light can be mixed with yellow light, and you can make white light, and I will not spend too much time on it. It has many, very interesting properties. Now, just like I told you, nanotubes need not be carbon, can have inorganic nanotubes. In the last 4 years, my laboratory has tried to do inorganic graphene analogs. Why only single sheets of carbon, non-carbon single sheets? Well, I show in the top left a high-resolution electron microscope image of a typical molybdenum sulfide sheet. Every atom can be seen there. It is aberration-free microscopy. And to the right, you can see that marked area, there is a single sheet of this molybdenum sulfide. And you can make a field effect transistor out of that, what I have tried to show here. So there are a lot of progress in this kind of work now. In the last 2 years, there are a spate of papers coming out on people trying to take other layered materials, make single layer or two layer materials, and look at them. There are lots of applications for graphene and other materials, applications of all nanomaterials. People have made sensors. I told you mechanical properties. Lithography, a lot of work on lithography, particularly in Northwestern. I'll show an example of that, dip-pen lithography, field emission in photovoltaics, a number of applications. I don't have time to talk about all of them. I'll just mention towards the end of my talk a little bit about hydrogen generation and storage. Dip-pen lithography is one that was originated in Northwestern by Chad Mirkin, and you can use the water meniscus that spontaneously forms between a scanning AFM cantilever, and in fact you can write all kinds of things. We can write, these are all lines, these are all 50 to 100 nanometer thick lines. You can do lots of nanography. This is one we wrote with iron oxide. The reason we did with iron oxide is because historically, prehistoric paintings are all in iron oxide. So I thought we should write something on prehistoric iron oxide. In Lascaux caves or in India, in Bhimbetka, to 15,000-year-old paintings are all iron oxide. Well, a lot of biological applications. I'll come to that in the end. Nanocrystal tagging. A lot of biology going on in terms of application of the sensor, of biological sensor, tagging, nanocrystal sensors for DNA hybridization, photovoltaics, again using polymer and along with the CDSC and such nanorods. A number of such applications have come in the last 5 to 7 years. Now, this is something I want to mention. The field effect transistors using nanotubes, they seem to be reaching a stage where IBM is doing very well. I don't know if you have seen, there was big news 4 days ago or 1 week ago, I don't remember, last 5-6 days, they've used carbon nanotubes, they put millions of carbon nanotubes and so on. I don't know, well, however, what they're going to do with the heat generated out there to find a way to get rid of heat that comes out of all this tremendous integration. But the wonderful field effect transistors have been made. This was the 2002 model of a carbon nanotube top-gated FET, but since then, a lot more progress has been made. Well, this is something of personal interest. We were the first to make a junction nanotube in my laboratory in 2001. You can see they're all Y junction. You see, the tubes are just straight tubes. You can have a T or a Y has a junction. At the junction, these nanotubes are transistors. They act like transistors. And IBM has used this also to make some nice devices. Well, lots of sensors have been made for gases, particularly by biological. I mean, the number of papers in application of biology and medicine for sensors, diagnostics is very, very large. Using, for example, I'll give you an example of a very elementary thing, zinc oxide. People don't look at zinc oxide. They make paints and people put their paint on their faces. But this zinc simple oxide has tremendous application in lasing, field emission. You can make transistors out of it, used for gas sensors. What I show on the top are the nanorods of zinc oxide. So tremendous applications. I'll spend 5 minutes, 2 minutes on this one frame. I took away all the frames because it will take a long time to explain each of them. I'm not a medical person. I'm not even a biologist. Biomedical applications are really fantastic. One of my very good friends, Mustafa El Sayed in Georgia Tech, and another person in UC San Francisco, they have used, for example, cancer hypothermia using gold nanoparticles, almost successful. This is in clinical trial. What you can do is you take gold nanoparticles, make it go to the cancer cell. As you know, the gold nanoparticles have a big surface plasma resonance, and you excite that, and the light is given out eventually as immense heat. The local temperature is very, very high. It really burns up all the cells. They've done a very, very good experiment. A lot of people have done that, but in principle, I would say Mustafa inside in Georgia and his collaborators in UC San Francisco have done that type of cancer therapy is common. A lot of MRI applications using magnetic particles. And tissue engineering, the most important example is the work of Robert Langer in MIT. Robert Langer has a huge industry going. I don't know how many industries he has. The number of things he has done, making artificial skin, growing spine, artificial spine, everything that you can think of. And he's very successful. And also, he's so successful, he has also made a lot of money, I think, in this. So tissue engineering has been very successful in the hands of Robert Langer and his colleagues. And that is, again, some of it is futuristic. But the fact is that the progress made in this is quite impressive, even for a person like me who is not in this field. Lastly, I want to refer to the very nice work done in Israel, in Haifa, in Technion, on the so-called nano nose. Shimon Peres, actually, the president of Israel, is the one who encouraged this. In fact, Shimon Peres, when I met him a few months ago, he was telling me, and this presentation of nano nose was made. This is a very interesting thing. We all breathe in and breathe out. We breathe out many molecules. I hope you all know that. Unfortunately, suppose you take what you are breathing out, suppose you get acetone. Everybody breathes out acetone. Nothing exciting about acetone. There are few unusual, unique molecules come out of the breath of a cancer patient. And what the wonderful work done in Technion is they have found that there is unique molecules can be detected. Suppose in breast cancer patient or lung cancer patient, what I have seen is very, very impressive. I must say it's really fantastic. This is a kind of a highly interdisciplinary area. The young boy whom I know very well in Technion, who started as a chemical engineer, he has worked with a lot of biologists and nano people, materials people. He has put up this fantastic demonstration, which is being now tested in a number of hospitals for just hold a breath and find out where you have what cancer, particularly breast cancer. It's been a great, terrific. I mean, you may laugh at it. It's not laughable. It's really serious. And that there are unique molecules that people breathe out depending on what cancer they have. And this is identified by the nano-nose. Well, I had an optical tweezer here. What I was trying to show was I was using to take a nanorod and interact with the laser beam, and the laser beam would interact with the dielectric of the nanorod and would give me some thing. Oh, you see that? That started rotating. You see, what I'm doing is a nanomotor, a nanorod, which rotates, and I can change the speed by changing the laser power. In space, it is rotating in space. It is not linked to anything. This is just an optical tweezer experiment that done a few years ago. I just want to show that. Well, I would like to end my lecture by saying some of the things I'm doing which I'm not talking about now. One is, can we make hydrogen using nanotechnology? As you know, President Obama gave one of the largest grants ever given of $120 million a few months ago to 3 friends of mine in Caltech and Berkeley. And we are doing very similar work using nanostructures, more than anything, artificial photosynthesis, where the catalysis is done by nanoparticles. This is one of the where we have had a lot of success in making hydrogen. And then storage of hydrogen in graphene. We have had up to 5 to 5.5 weight% graphene. The Department of Energy in the US wants 6.5 weight% for running cars and planes and so on. But I don't know whether they'll use graphene, but chemical reversible storage of hydrogen is another area we have done a fair amount of work. And lastly, the entire area of energy and environment and a number of areas like this, I think the nano materials will play a certainly important role. If we can succeed making hydrogen the way we think we may succeed, I think it will be a tremendous contribution, because hydrogen will in fact contribute in a big way to our future energy needs. I would like to thank you for your kind attention.